hello together also from my side. My name is Christopher Stang. I'm an employee at the Friedrichshafen AG, as you can see on the logo, as well as I'm a PhD student at the Technical University of Munich. And today I would like to give you some insights about the paper I've written. It's about the calibration of microscopic traffic simulation in an urban environment using GPS data. So let's have a look at the agenda for today. First of all, I would like to give you a short introduction, background of the work. Then we will have a look at the network that was considered within this work before we talk about the methodology and also about the simulation results. And last but not least, a short conclusion and also an outlook for the future work. So let's go to the introduction. So, we all know accurate traffic models, they are very important for well-founded traffic engineering. And there's a common approach of how to calibrate microscopic traffic simulation. You can use traffic count or speed measurements of different road segments. This is a common approach, and in this respect, SUMO offers some tools for calibrating microscopic traffic simulations on the basis of count measurements and for generating traffic demand models. And these are basically flowrouter and routesampler. There have been also the aforementioned, but for urban scenarios, it's not that practical, to be honest. And but today I don't want to speak much about flowrouter and routesampler, even though they are part of the analysis. I really want to show you the methodology, the extended methodology. It's a two-step optimization process, and it's a two-step optimization process on the basis of vehicle and count measurements. The count measurements, or the source of the count measurements, they can be manifold. They can range from manual counts, they can range from induction loops, and in our case, they came from GPS data provided by TomTom, but not for free, of course. So we had to pay for that. So I already mentioned it is a two-step optimization process. Namely, it consists of an a priori optimization, especially of the count measurements by adopting integer linear programming. And the second step is the a posteriori optimization, especially of the speed data, by adopting a combination of integer linear programming in combination with an evolutionary algorithm. So a priori optimization here means that you optimize before any simulation process has been done, and the a posteriori optimization directly uses the simulation results to calibrate your model. So let's have a look at the network. Of course, we considered Friedrichshafen, so to promote Friedrichshafen a little bit here. You can see here on the left-hand side the subnet-work with its main track of Friedrichshafen that was considered for this analysis. The main track has a length of approximately 3 kilometers, and we got some data set from TomTom containing information about the vehicle counts and speed measurements. In some, the data set contained information for 100 road segments, and as each road segment can be interpreted as switch or detectors, I would say. I also will call them detectors in the following explanation. So in some we had 100 detectors distributed along the track for a time frame of 36 months, ranging from the years 2017 to 2019. And the data set, it was already aggregated. It was aggregated in a way that we have one representative working day and one representative weekend day of each month of each year, and each day again was subdivided into 12 time intervals with an interval of 2 hours. So the basic question now is, what is the best approach to set up a realistic traffic simulation with the existing data set? Well, I've mentioned there are the tools flowrouter and routesampler, but of course we will have a look at our developed methodology. So you can see here on the left side the workflow of the methodology, which consists mainly of 5 parts. First of all, of course, you have to set up a network for the SUMO simulation, otherwise you cannot do any SUMO simulation. Then if you have no idea about the trajectories, the real trajectories, then the best idea is to generate some random troops, and you can do this with random trips, of course. Then the next step would be the a priori optimization of the vehicle count measurements, followed by the posteriori optimization of counts again, but especially for the speed data. And last step, of course, is the comparison of the simulated results with the real traffic data. So the first two steps, they are the easier part of the work. Again, here you can see the map coming from OpenStreetMap, and the generated SUMO network with its main track, and also the adjacent access and exit route of the main track. Okay, let's come to the methodology, to the first part of the methodology, the a priori optimization. So, having generated a set of initial routes, unique routes, you can formulate the mathematical problem in a way. How often does every of these routes have to be chosen to match with the real vehicle counts? And I would like to give you also some insight in the math behind it, because in my opinion it is very important to understand that. So, but the problem that I formulated, it can be solved with conventional integer linear programming. So we have an objective function, and we also have some inequality constraints. So let's define these inequality constraints. I will keep it as simple as it is. The lower limit of the inequality constraint will be set with a zero vector according to the number, with the size according to the number of the detectors. In our case, it have been 100 detectors. The upper limit, it will be set with the real recorded vehicle counts for each detector, again according to the number of detectors we have. So the more complex step is the definition of matrix A. It is a two-stage process. First, we set up an auxiliary matrix, A slash, I will call it A slash, with m rows according to the numbers of detectors we have, and with n columns according to the numbers of unique routes that have been generated by random trips. So, and for each column of matrix A slash, the detectors are placed in the same order for each column. So each column can also be interpreted as a representative of each route that was generated. And the next step, it is just simple. You run through each column. You run through each column and check if the route or which detectors are contained for each route. And if this is the case, if one of the detectors is a part of each route, then the corresponding detector edge will be set to 1 and otherwise to 0. So the output of A slash is matrix A, and matrix A is nothing else than an indicator if the route contains one detector or not. Okay, so with the definition of A, the decision variables of matrix, or of the inequality constraints, the decision variables X, they can be interpreted as the multipliers of each route, as I announced before. How often does every route have to be chosen to match the real vehicle counts? So X are the multiplicators of each route to match the real vehicle count, but it's still left to define the objective function of this problem. And it can be formulated in an easy way. The objective variables of the objective function, they are nothing else than the sum of each column. And the maximum or the optimization problem is formulated as the maximization of all vehicle counts along all routes. And since we want to formulate a minimization problem, well, you can do it just by multiplying it with -1. So what you have to keep in mind is, from all the mathematical stuff, we have a set of initial unique routes. We multiply them by considering the inequality constraints, and we optimize the sum of the vehicle count along all routes to match the real vehicle data, real vehicle counts. So at this point, I think it does make sense to have a look at the first results of the a priori optimization. And yeah, first of all, I would like to say that we've also depicted the corresponding results that have been produced by flowrouter and routesampler, and these results have been compared to the integer linear programming algorithm. And I think we also have to differentiate between pre and post simulation results. Pre-simulation results, these are the direct result of adopting any a priori optimization technique. That means these are the simulation results before any simulation process has been carried out. And the post-simulation results, of course, these are the results that have been produced by the traffic simulation. So let's focus on maybe on the upper diagram. As goodness to fit measurement, I have chosen for the vehicle counts the mean absolute error. You can see on the x-axis the 12 time intervals. And for a better understanding of the traffic demand in general for each time interval, I've also included the mean recorded counts along all detectors. So you get an impression about the development of the traffic demand over time. And what you can see here is that we get a really good match, here the green line, that we get a really good match for the pre-simulation results for the ALP algorithm. But as I already said, we also have to take a look at the post-simulation results, because any a priori optimization technique, especially integer linear programming, it cannot take into account the traffic dynamic that is a result of a traffic simulation. That means, I mean, there can be traffic jam, maybe as a result of any actuation of the traffic lights. I mean, it also could be possible that a route is generated in the preceding time interval, but ending in the subsequent interval. So you also have a time overlap of routes. And this is the reason why you also have to take a look at the post-simulation results. And the post-simulation results, they also show bigger deviations. We have bigger deviations for the mean absolute error for the vehicle counts. But as you can see here again with the green line, we have a lower mean absolute error for the ALP algorithm. So even though it is not focus of the ALP algorithm, for the sake of completeness, I also depicted here the mean absolute error for the speed data for each time interval. Yeah, because it's not a part of the integer linear programming algorithm. And since it is not a part of the a priori optimization of the integer linear programming algorithm, you have to think about how can we calibrate the speed data that we have. And with that in mind, we came to the conclusion, okay, we need an a posteriori optimization. This is the idea of the a posteriori optimization, to calibrate the speed data, because the resulting speed data is a direct result of the traffic simulation, of the traffic dynamic. And for this reason, we formulated the mathematical problem by a combination of the aforementioned integer linear programming combined with an evolutionary algorithm. And the workflow you can see here on the right-hand side. First of all, we start, of course, with the input, with the empirical data provided by TomTom. We generate an initial population by adopting the integer linear programming. Well, the initial population firstly just consists of the multipliers of each road. And this parameter set is extended by the maximum allowed vehicle speed of each detector. I've chosen the maximum allowed vehicle speed of each detector because everybody who's driving a car regularly knows that you don't drive 50 kilometers per hour when it's set to drive 50 kilometers per hour. So this is my instrument to calibrate the speed data. Then we have to calculate the objective, which in our case is the mean absolute error for the speed. And also we have the option to further improve the vehicle count data. We check the termination criteria. If termination criteria are fulfilled, then everybody's happy, then calibration is done. This is a typical calibration process. If termination criteria are not fulfilled, then we have to make an optimization iteration. And for this reason, I've selected the typical elements of an evolutionary algorithm consisting of the selection process, recombination process, mutation, and reinsertion process. So selection process means that we select the best parameter sets after each optimization iteration that have led to the least deviation for the mean absolute error for speed and counts. We recombine them in a specific way, mutate these parameter sets within a specified range before we reinsert them into the initial population. And we do this until we reach a good fit with our input data set. So, with all this mathematical background, we now can have a look at the results of the a posteriori optimization. You can see here the simulation results again of the a priori optimization. And for the application of the a priori optimization and for the application of the a posteriori optimization, we selected one time interval with sufficient travel demand, because it's more sophisticated than to choose a time interval with less travel demand. You can see here on the right-hand side the results of the a posteriori optimization. Direct comparison just by adopting the integer linear programming. And firstly, as I announced, as it also is considered within the evolutionary algorithm, we could reduce, again, the mean absolute error for the vehicle counts by minus 10%. And for the speed data, we could reduce the mean absolute error by 21%. So we get a better correlation with the real data set. Okay, this leads me to the conclusion and to the outlook, to the last part of this presentation. Well, what I wanted to show you was the two-step optimization process for the calibration of microscopic traffic simulation. And as you could see, we adopted a two-step optimization process consisting of the a priori and a posteriori optimization. I've shown you a showcase for a subnet-work of Friedrichshafen for a specific data set, the method it was implemented and tested, and also compared to the tools SUMO provides, to the ready-to-use tools SUMO provides, namely flowrouter and routesampler. And we could, for this showcase, produce better results than these tools. Maybe as an outlook, because we just adopted it for one single time interval, the idea is, of course, to extend the method of the a posteriori optimization for a larger time frame, and maybe also for more days, to get a very realistic traffic simulation for a large time frame. And maybe as a midterm or long-term outlook, since you have a possibility to calibrate your models, your traffic simulation models, it also offers the possibility for the so-called traffic-based testing. Traffic-based testing, it is the counterpart of scenario-based testing, where you just focus on one specific scenario. Traffic-based testing means that you can investigate the traffic dynamic and also the change of the traffic dynamic if you want to develop any ADS or ADAS function. So if you want to investigate the impact of such developments, you can directly compare it with the reference that can be produced or generated with this method. And this would be all from my side. And perfectly in time.